Hello everyone. In this video we are going to talk about the K-nearest neighbors method, or KNN, which you can use for classification or regression. This is one of the simplest yet very effective methods of supervised learning, because in addition to the raw data you also provide a label for them. So when you have any data, you know what kind of class, let's say if you use it for classification, it belongs to, or what is the value of it if you want to do regression. So it's definitely a supervised method, and it's non-parametric, means when you do the classification or regression, you are not assuming any model here, and you are not going to find any parameter for it. You have no prior information about the data, and that's one of the advantages of this method, that it does not need to basically find a model, to define a model or anything, or have any a priori information. And all you do is basically you look at the surrounding of the data, the local data around your point of interest, and you determine the class of this new data, or the value of the output at this new data, basically locally. So all that matters are the neighbors, and not all of them, only the k of them that are the closest. Now, what is k? K is the only value, the only parameter in this machine learning algorithm that you choose. Is there an optimum value for it? We'll see. Yes, kind of. And we'll talk about it. But first, if I want to show you a very, very simple example. So let's say here, I have two classes of data, the blue squares and the red triangles, right? Two classes. Then I go ahead and have some new data, the green circle. If I want to say whether this green circle is a triangle or a square, what do? I look at the k closest neighbor of that. So here, depending on what this k is, for this solid circle, k is 3. Out of all points that I have, triangles and squares, I look at the 3 of them that have the smallest distance. They are the closest, which are going to be the 2 triangles and the square. And then I say, well, around this guy, 2 are triangles, 1 is square. So if I want to go with the democracy and get some votes, I have 2 votes for being what? A triangle, and 1 vote for being a square. So I vote for what? A triangle, and then say, hey, this guy is going to be what? A triangle. I classify it like that. If I change my k now and say, well, maybe I go with k of 5. So now I look at the 5 closest data points, which this time is going to be 3 squares and 2 triangles. And again, if I want to go with the democracy, now I have 3 squares versus 2 triangles. So this time I have to say this guy is a square. So clearly you see that the number that you choose for k would definitely affect what you get out of the classification. Okay, or if it's regression, now you might say, well, how would you do regression? In regression, instead of me having a class for this data, I have some values for the data. So for example, instead of being what? Being a triangle, the value instead might be like 5, and if it's a square, it could be like -2. So I want to know whether this point is -2 or 5. Then again, if I go based on the value, I should say it's 5, or I might what? I might take the average of these numbers. If because when it's a class, it's either class 1 or class 2 or class 3, right? But when it's a value, you can have decimals. So this time, maybe I say, well, the value here is what? Is 5 plus 5 plus -2, and then maybe what? Divided by 3. Okay, so I can do an average of them, or I can do, well, as we'll see, a weighted average of this data. So I can do classification or regression. Here we mostly talk about classification, but again, as long as you have values for this point, you can also do regression. And it's all local data that has the final say. Now, some important things about this very intuitive and yet simple method, but effective, is one, since it relies on the distance. Remember, you're talking about the closest, and close means what? Or nearest. Near or close means the smallest distance. So one important thing is, sometimes this data that you have, they come in different scales. If they do, and then you don't normalize, then it can completely affect the final results. Just for the moment, assume that all of these squares are like in tens, so they are like 10s, 20s, 30s, 40s, while all of these triangles are in ones, so they are one order of magnitude smaller, so they are like 1, 2, 4, 6. So now if you choose any point here, depending on where it is, because these squares have an order of magnitude larger scale compared to the triangles, you will easily be either next to the triangles or next to the squares, and these data are not going to be clustered like this. For example, if I do it with the same way that I mentioned it, and I plot it on a 2D graph, what would you get? Let me show you that. So you will be getting, let's say, these triangles here. But then the squares will be way out, like here. Okay, so that's the problem of scaling. These are 10 times, let's say, on average, bigger in the scale compared to the triangles, and that's where normalization comes into play. What does normalization mean? It means you can divide, for example, all of this data, let's say they're x1, you can divide them by the maximum of the x1 they have, and you can do a similar thing on x2. Now, that's not necessarily always the best normalization, but many times that's what you do. So you make them only range from what? 0 to 1. And you do the same thing for the squares, so now the squares will fall in the same region, and that makes what? That makes a plot like you can see on the left. So normalization would take away the problem that comes with different scaling and different units. And it's always recommended that we take advantage of it, otherwise the final output of your KNN will be completely biased. What else can affect the performance of this method? The other one is outliers. Outliers, you know, especially when you're using Euclidean distance, the outliers are not your best friends, right? If you have one of these squares all the way down here, right, as long as you're doing your basically finding the class of data in this region, that guy has no say, because it's not close to any of what? Any of the new data you're trying to classify, right? So literally it's like throwing it away, right? And if you have more of that, let's say out of the 6 squares, now 3 of them are all the way down here. Instead of being these 3, they are all the way down here. So literally in this region, as I said, inside this circle, these guys play no role, and that might not be necessarily a good thing, that a bunch of data from one class or maybe a few classes have no say, right? Because they are outliers. Now, of course, when you come close to this region, it's only the outliers that have all to say, and the rest of the data have no say. So that's the worst part, actually, as long as you are close to this region of the data. Because remember, when you have outliers, your classification region becomes much larger. So now, as long as you're close to these outliers, the rest of the data have almost no say. So any data I put around here will definitely be recognized as a square, because all the other squares and triangles, especially triangles, are completely off. So the outliers will definitely shift the classification regions, or you might want to call the decision boundaries, and that's our next topic, the decision boundaries. They would definitely change these decision boundaries, which are the regions that on the two sides of it you have class 1 versus class 2, right? And you can see them here in this picture, right? The red region versus the blue region. If you have outliers, they significantly shift these boundaries of your classes, or decision boundaries. So one of the things that they typically do with KNN is first they do an outlier analysis and outlier removal. They try to get rid of the outliers if they can, so that the boundaries are more robust to and more revealing of the actual classes. Now, since we talked about this decision boundaries, let's take a look at them. So this decision boundaries, these are the data that will, not the data, these are the edges, the boundaries, that on one side of them you have one class, on the other side you have another class, right? The boundaries between the classes. And here, the example that I'm showing you, I have a bunch of triangles almost on the upper half of this search region, and a bunch of circles on the lower part. Now, there are some data that are not sticking to the rest. For example, here, this circle is very close to a bunch of triangles, and this triangle is close to a bunch of circles. So there are some areas that the data, the classes get close to each other. Good. And now you might wonder, how do I get these boundaries? I'll show you. I have written a sample code, a demo code, that, by the way, I will share with you the link for downloading it in under the video description. And one thing that you would definitely see, first of all, after you see that when K changes this boundary, the shape of the boundary or the edge would change. The second thing is when K gets larger, your boundaries kind of get smoother a little bit, okay? And that's another thing that I mentioned here, because when K gets bigger, basically you have a lot more data, and many of this data would tend to kind of cancel each other's vote. So the final vote that you get is kind of like an average vote of a bunch of data, not just a few select data. It's not going to be so limited and so local. It's a little bit more global now. And so a bunch of data are now going to play the role in determining the final class of the data. So it is going to be smoother, right? And not prone to a few outliers or just some local changes in the structure of the data. So bigger K's typically corresponds to what? They correspond to smoother boundaries. Now, how do I generate this graph that you can see here? So there are two ways you can handle it. You can either write your own code, which here I did for you, Or you can use the built-in function in MATLAB if you're using MATLAB. So for MATLAB, there is this function KNN search. You pass to it your data, and here your data includes the observations and the labels. And you pass to it the new data, and then it gives you the class or the value for this new data or the vector of the new data based on the training data. You pass to it the value for k, and the other thing you can do is the distance. For the distance, not only you can use Euclidean distance, you can use all other functions that I mentioned in my previous videos, like the Chebyshev, right? Which is basically, you have Chebyshev norm, you have Manhattan norm, or L infinity and L1 norm. You have the Minkowski or P norm, and if you use P norm, you have to provide the value for P. If this P is equal to 2, you get back your Euclidean distance, okay? If you don't provide a function for the distance, it uses Euclidean distance or 2 norm, basically. And if you don't provide a K, it probably will consider some K of default, but you have the option to use the MATLAB default function, KNN search, which is under statistics and machine learning toolbox, or you can write your own code. So here I did it. So here I define my X values. My X observations have 2 entries, X1 and X2. So I have 2 variables for each data point. And then I have a bunch of labels, 1 and 2 really, 1 for the triangles and 2 for the circles, okay? Now what do I do? Here I'm allowing you to choose the value for k, and also I'm allowing you to choose an option. This option is 0 or 1. What is 0 or 1? Let me discuss it first before I go and show you the rest of the code. So if you do the KNN in its original format, all you do is you look at what? The classes or the values of the closest neighbors, and basically their vote is gonna be like a 1 or a 0, right? So what do I mean? As long as they are in the region defined by k, their votes is like 1. If they are falling outside that region, so if here I only want first 3 neighbors, closest 3 neighbors, nearest 3 neighbors, those have a vote. Anybody outside that are not the 3 closest, they get a vote of 0. They won't be heard, basically, right? And here, these 3 neighbors that have a vote, their votes are counted equally. All of their votes are 1. All of their votes are 1. So basically, it doesn't matter between these 2 triangles. One of them is closer than the other one. They both count as a 1, and this square which is further away compared to both of them, again, that also doesn't matter. I just count. Hey, I have 2 triangles, 1 square. The triangles are the winners. I don't care how close they are. Most of the time, this might not be the best approach because the distance could play a significant role. So if we want to bring in the effect of the distance as well as what class these data are, then I say, well, this data that is the closest to the circle should have a bigger say. This triangle, a little bit smaller, that square, even smaller, right? So if that's the case, then maybe I don't give them all a weight of 1, or let's say if I give this one a weight of 1, this one maybe I give a weight of 0.8, and maybe this one 0.6 or 0.5. Okay, and how do I do it? There are too many different ways, but basically the goal is this. If you call this point vector x, and if you call this training data xi, correct? The weight of that data xi should go what? Up when the distance between that xi and x is what? going down. So the closer you are, the bigger your weight is going to be. And then one of the simplest cases that you can consider is if you want the norm to go down, the weight to go up, you might say, well, how about I do it like this? I say this weight is simply 1 over the norm, right? And that is exactly what here we discussed in weighted KNN. So this is this formula. The value estimated does not simply come from a majority vote. You can weight basically the value of the labels by the reciprocal of the distances as weights and add them or something like that. And you might say, what's the effect of that? Here you can see in these two pictures on the left and right we have both k of 9. On the left we have basically every data in the circle of k-nearest neighbor, their vote counts equally, so their votes are all 1. And one of the things you see is a misclassification. You see here this triangle is classified in the blue region. Any data in the blue region belongs to the blue circles. And one blue circle is classified as triangles. Any red point belongs to the red triangle class, right? So here you have misclassifications. While here, if I used the reciprocal weight, as you can see, I have what? I have that misclassification fixed, so now it belongs to the triangles class, and there is this small blue island within the red region that the data correctly is classified as what? As a circle. Okay, so this weighted average typically intends to improve the performance of the k-nearest neighbor, and many times using a function other than Euclidean can make the algorithm and the result more robust to outliers if you haven't done outliers. But it's always, as I said, is suggested that you first do scaling and normalization, and second you do what? Outlier analysis for this KNN, and then it is better to use what? The weighted KNN instead of just the simple KNN. Okay, so here we have seen that K has effect, right? K has effect on the decision boundaries, as well as whether you use a weighted approach or just the simple counting all votes equally. Now, the next important question that comes into play is which K is the correct K? Which K is the appropriate, the optimal K? We learned that when K gets bigger, the data gets smoother. But fine, should I always go for smoother boundaries? Well, not necessarily. So one thing is this. As K gets bigger and bigger, the change in the boundaries gets smaller and smaller. I mean, if you go from here, K of 1 to K of 5, you see some significant changes in the boundaries. When you go from 5 to 9, you see that the boundaries have changed, but not as dramatically as you went from 1 to 5. And if you want to do this one more time, and maybe you go from K9 to what? Here I went up by 4, so maybe if you do it next time for 13, if you do that here, and I'm going to do it for you, I'm going to run my code, the boundaries are almost the same as 9. So after some K, you don't see any major shift in the boundaries. Whenever the boundaries start to kind of go fixed and not change beyond some value, you can say that value is what? Is an upper bound, correct? That is an upper bound for your K. You should not really go beyond that. If I go above k of 9 and I don't see any major shift in the boundaries, why should I increase it? That's the upper bound. But does this upper bound necessarily mean that's the optimum value? Well, you know, the bigger k that you use, the more computation you have to do, correct? You have to look into k nearest neighbor where k is large compared to only look at 1 or 2. So when you go this way, you have more computations. So where is it that you want to not go any further up and save on the computation? What is the optimal value for k? For that, you can look at what? The accuracy of your classification. I mean, if you look at here and here, you might say, well, if I look here properly, these two data, look at these two data. If you look at these data here, this red kind of falls on the boundary, this triangle. This circle falls in the wrong region for k of 5. If you look at k of 9, definitely the triangle is in the wrong region and the circle is in the wrong region. For k of 1, they are right. They are in the right region. In other words, there is no misclassification for k of 1, but there is some misclassification for k of 5 and k of 9. So one way that you can look at it is by the results of the classification. Remember, this is a supervised method. You have tag, you have data, output data for the circles and triangles. So what you can calculate is a confusion matrix. Remember confusion matrix, the true negative, true positive, false negative, and false positive. If you look at them, and you can also look at those rates. Remember, in one of my previous videos I introduced several rates for you: the recall, the precision, the accuracy rates, right? There are so many rates, and at the end I mentioned you can combine them all using the Matthews correlation coefficient, MCC, to see, based on this parameter k, which one is giving you basically more accurate predictions, better classifications. So you can take a look at that and see which one of them is giving you. Apparently here k of 1 is doing a better job than the rest of them. And again, if your goal is, hey, I don't care about the smoothness of the boundaries, my data is only the data that I see, then sure, for the moment being, K1 could be better than the other case. What's the problem? The problem is when you introduce more data. When you introduce more data here, then it is what? It is the small k's that will go through a dramatic shift in the boundaries. These guys, which had already big k's, they change margin, they change very insignificantly. So when you go that way, you have more computation, yes, but also your robustness to introducing noise in the data, to introducing more training data, and so on goes up. Does necessarily accuracy go up? Maybe, maybe not. And again, you can see here that what? That using a weighted average instead of just using all votes equally would make a big difference. Here with k of 9, I have the misclassifications, but with the same k of 9 but weighted average, guess what? I have absolutely no misclassification. So maybe as long as I use proper weights, I do not need to just keep going up with k, right? So deciding on a proper value for k and optimal value for k can be done by confusion matrix, the robustness of the boundaries, and so on. And since here I promised you, this time I change it to 13 and I turn this option 0 because these three graphs were all obtained by no weight. Okay, so here I'm going to run my code for k of 13, and I'll show you how the boundary would look like for k of 13. That would be nice to see whether you see any major shift after this k of 9 or so. And while that plot is being generated, there is one more thing I wanted to mention as the last point. Sometimes, because the KNN method is a computationally demanding method, it could be very slow and very demanding. One of the things that some people do to accelerate this is they reduce the total number of training data that they have by something they call data absorption. And what is this data absorption? So here they're not going to use each and every one of these training data. Instead, they use a subsample of the data, and as long as that subsample of the data is enough to accurately predict the class of all of the data, right, then basically generating the same decision boundaries that you have. Instead of 100% of training data, you can generate these decision boundaries by something like 50%, 60% of the data or so. Then they basically use only that 50 or 60%, and they are not going to use all of the data. Why? Because that way they can reduce the size of all of those distance vector that I showed you in the code, and that brings down the amount of computation. So if I want to just briefly tell you the advantages and disadvantages of KNN, the good thing about KNN is actually it's quite accurate, although it's very simple, yet very effective and accurate. The big major thing is it does not need a model or any prior information or anything. It does not make any assumption about the data. The bad thing about it is it can be slow and computationally demanding, especially when you have a ton of data. As long as you don't do this data absorption, you see that the code runs quite slow. Here, my laptop is a Core i7, and it's not bad in terms of cache and RAM and everything. But with only here, 25 data points, generating this plot took quite a bit of computer time, as you just saw. And here, this is k of 13. For some reason, it's not showing the number 13 here, but if you put it, let me see if I can shrink it down. If you put it next to k of 9, then you see that there is some shift in the boundaries. Still, there is some shift in the boundary, and it's mostly this region on the left, but it's not as significant as when you jump from k of 1 to k of 5. Now, if you go further up, this amount of shift that you see here in the left region will also subside. But it's another interesting thing. If you look here now, with k of 9, I had what? I had one misclassification here, one circle, one triangle. Now another circle is falling on the boundary. So it means I'm going up with k, but my misclassifications are going up too, or my accuracy is falling. So please keep that in mind. Bigger value of k by no means necessarily imply better accuracy. No, it means just more robustness to the boundaries of the classes or the decision boundaries. It doesn't mean you're doing a better job. Unless, as I told you, use what? Use this weighted average or something like that, weighted votes, basically, that can generate better results. So hopefully this simple video on KNN was useful to you. And as I said under the video description, I'm going to share my own code with you, although you can always use KNN search in MATLAB. Now, of course, for it, you have to have the toolbox of statistics and machine learning. Not everybody does. So find it and download it under the video description. Thank you so much. I will see you in my next video.